All right, let's talk about some of the most overlooked but honestly most fascinating characters in all of chemistry. We're talking about the F block elements. The ones that are kind of hiding in plain sight at the very bottom of the periodic table.
Yeah, you know exactly the ones I'm talking about. They're always set apart, almost like an afterthought. Well, today we're finally pulling them out of the basement and putting them right in the spotlight. What are these things, and why in the world are they so different? The best way to really get a handle on these elements is to use a simple analogy. Just imagine these two rows are two very different families, the lanthanides and the actinides. They might live in the same part of town, but trust me, their personalities couldn't be more different. Okay, first up, let's meet the lanthanides. If these elements were people, they'd be the quiet, predictable, and frankly, remarkably stable members of the family. They really like to keep things simple. So what actually makes a lanthanide a lanthanide? Well, it all comes down to where their electrons live. Think of an atom like a huge apartment building with different floors or energy levels. For these 14 elements, the new electrons don't move into the fancy penthouse suites. Nope. Instead, they start filling up a deeply buried, super secure inner floor called the 4f orbital. This is their core family trait.
And because those new electrons are buried so deep inside, the lanthanides have a favorite way of reacting. It's what we chemists call an oxidation state. And for pretty much all of them, it's a simple +3. This just means they prefer to give away 3 electrons to become perfectly stable and predictable. It's their signature move, their comfort zone.
Now, even in the most stable families, you've got a couple of siblings who'll bend the rules, but only for a really good reason. Take cerium, for instance. It can actually reach a +4 state. Why would it do that? Well, by giving up that extra electron, its 4f orbital becomes completely empty, which is a super stable situation. Same thing with europium. It can go to a +2 state to get a perfectly half-filled 4f orbital, another little island of stability. So the key here is they only break their +3 habit if it makes them even more stable.
All right, every family has its quirks, right? And the lanthanides have a really interesting one that has these huge consequences for the rest of the periodic table. It's called the lanthanide contraction. It sounds complicated, I know, but the idea is actually pretty simple. As you move from left to right across the lanthanide family, each element gets just a little bit smaller than the one before it. It's this steady, predictable shrinkage. But why? Okay, let's just walk through this. With each new element, you're adding a proton to the nucleus. That makes it more positive, so it pulls harder on the electrons. Simple enough? And that new electron, it goes into that deep 4f orbital we talked about. Now, here's the interesting part. Step 3, shielding. Think of inner electrons as bodyguards, protecting the outer electrons from the full pull of the nucleus. Well, the 4f electrons, they're terrible bodyguards, absolutely awful. Their shape is so spread out, it's like trying to block the sun with a chain link fence instead of a solid wall. The result? That increasingly powerful nucleus just yanks the outer electrons in tighter and tighter, and the whole atom actually shrinks. And this right here brilliantly illustrates the consequence. Check out zirconium and hafnium. Hafnium is right below zirconium on the periodic table, so it should be way bigger, but it's not. It's almost the exact same size. How is that possible? Well, it's because that lanthanide contraction shrunk all the elements leading up to hafnium so much that it completely canceled out the size increase you'd normally expect. It's a truly wild ripple effect. Okay, let's move on to the other family now. If the lanthanides are the stable, quiet siblings, then the actinides are their energetic, restless, and, let's be honest, much more complex counterparts. This is where things get really wild. Their whole identity starts with filling the 5f orbital, which is further out and way more energetic than the 4f. But their real defining traits are these. Every single one of them is radioactive. Most of them decay incredibly quickly, and a lot of them don't even exist in nature. We actually have to make them in labs. Bottom line, they are fundamentally unstable. And you can see this instability written all over their chemistry. Remember how the lanthanides loved that cozy, stable +3 state? Yeah, the actinides basically took that rulebook and threw it out the window. They are so much more flexible and willing to adopt a huge variety of chemical identities. I mean, just look at this range. They can go all the way up to a +7 oxidation state, which is just incredible. Elements like neptunium and plutonium can pull this off. They're also really good at forming these special teams with oxygen called oxocations. You can see one of the most famous ones right there. This kind of complex reactive chemistry is something the lanthanides just don't do.
So we've met both families, the quiet, stable lanthanides and the restless, wild actinides. Now let's put them side by side for a little family showdown to make their differences crystal clear.
This table just sums up their different personalities perfectly. Lanthanides fill that deeper 4f orbital, actinides the more energetic 5f, and pretty much everything else flows from that. Actinides have a much greater tendency to form complex molecules. And look at the color. The quiet lanthanides are mostly colorless, while the flamboyant actinides are often brightly colored. It's the perfect visual, right? The quiet siblings versus the restless ones. So after all this, you might be asking, okay, cool, but why does this matter? Are these just some weird footnotes in a chemistry textbook? Absolutely not. These hidden families have some seriously important real-world applications. For the lanthanides, since they're all so chemically similar, separating them is like trying to sort a bag of nearly identical marbles. So we use special molecules like EDTA. It basically acts like a tiny, precise chemical claw, grabbing onto specific lanthanides just enough to pull them apart. And on the actinide side, their intense energy can be harnessed for good. That radioactivity, for example, allows an element like radon to be used in tiny, targeted doses for radiation therapy, fighting diseases like cancer.
And that brings us to the end. We've got these two very different families, one that's stable, predictable, and subtle in its influence. The other, energetic, complex, and incredibly powerful. So the question I'll leave you with is, as we continue to explore the building blocks of our universe, which of these families, the quiet one or the restless one, do you think holds more secrets for our future?